Welcome to this unit on flexible particles and structures. This unit will go significantly beyond standard DEM applications. But before we look at the topics that we discuss, let me introduce what you will learn. First, and as already announced, we will have a look at typical applications of flexible particle and structure models. What we mean with flexible particles is illustrated here on the right. In contrast to the classical soft sphere DEM, the particles we simulate deform physically, meaning that in addition to the contact force model that assumes deformation only at the contact points, also the particle itself deforms. As you can imagine, this requires a significantly more involved approach, and this is also why we have added this unit to our MOOC. However, it also opens the opportunity to model flexible structures or walls. You will see that our unit is a door opener to many applications that are simply infeasible with other methods. Great power means great responsibility, and consequently there is a plurality of flexible particle models out there. Unfortunately, our time is limited and we have to focus on one of the available models, which is the bonded particle model, or short BPM. You will see that with the bond types that are available in a BPM, we can model a wide palette of particles and structures. To conclude our unit, we will finally look at wave propagation through a 1D flexible particle. This background will help you to select an appropriate time step size in flexible particle DEM simulations. Let us now start with an overview of applications in which flexible particles and structure models are used. The first group of applications is the modeling of fiber and platelet-shaped particles, i.e. one- or two-dimensional geometric bodies. We have seen the first concrete example already in our introductory unit. These are agricultural machines such as the straw or hay conditioning machine here on the left. This impressive work from Becker 3D highlights also an important feature of flexible particle models. This is the ability to add features of permanent, meaning plastic deformation, or even particle breakage. While it is impossible to model breakage in the classical DEM, there are ways to do it in a conventional DEM-based simulation. However, flexible particle models are predominantly used in case the breakage process should be predicted as precise as possible. In the same group of applications are pulp and paper applications, e.g. studies of pulp flow or simulations of the sheet formation process to produce paper. The next flexible particle simulation application area is the bioenergy sector. Think of the behavior of wood chips or straw. Also, crystals are an important application of flexible particle models, not so much because of their deformation, crystals are quite stiff, but because needle-shaped crystals can easily get broken in industrial processes. This causes attrition, which is an issue that needs to be avoided. In case we think of fibers in a more abstract way, we will find that we can use them also in larger scale applications, e.g. to model ropes, nets, or barrier systems that often consist of ropes and flexible ring structures. The next applications include membrane structures. As you can see on the left, membranes are an important part of belt conveyors. In the insert you can see the structure of a bonded particle model that represents such a belt. Clearly, it is a two-dimensional network of particles connected with bonds that is used to discretize the membrane. On the right-hand side, you see a membrane that is deformed in an extreme way and for which a vibrational analysis has been performed. At the top you see the belt colored by the local membrane velocity due to these vibrations. You can imagine that due to the highly complex deformation of the membrane, also the oscillation behavior is non-trivial, as illustrated by the complex structure of the membrane velocity. Also, more complex structures can be analyzed with membrane models. For example, so-called sandwich conveyors, which are able to transport granular material vertically upwards. How this amazing machine works is nicely illustrated here in the video of Eric. As you can see, we have multiple membranes in this simulation, and the beautiful thing is we can predict the strain and stress in each belt of the conveyor. This is very useful for picking the optimal material for such applications or optimization studies of the pulleys, for example. Next, we shift back to agricultural machinery equipment, for which you see a beautiful application here on this slide. As you can see, we have flexible fiber-like particles and a flexible membrane in this simulation of a straw bale press. Note the fibers are colored according to their age in the simulation. This allows a visualization of how the straw bale is formed inside the machine. Also, if you look closely, you can see that the membrane is colored differently, indicating that this simulation has been used to assess the stresses in the belts that drive the bale. Also, similar applications can be found in the pulp and paper industry, in which dewatering of the freshly formed paper is initially performed by so-called presses that also contain membrane-like structures. The next set of applications is a bit closer to our daily life. These are transport and storage containers, as well as the plurality of packaging materials for solids and liquids. As you can see in the video on the left, in such simulations it is quite easy to impose complex boundary conditions, such as the moving transport pallet here, or to visualize the stress in the membrane that forms the bag, or also what happens with the material inside this big bag. The third set of applications contains materials that undergo extreme deformations. A typical example are comminution devices, such as the jaw crusher here on the left. The purpose of such crushing simulations is twofold. First, we can identify the product size distribution, and second, we can also understand the location and magnitude of forces that are acting on the machine. Clearly, such simulations may be very helpful to optimize such processes and save valuable resources, e.g., by an optimal reinforcement of the structure of the crusher. Other examples in this context include rock mechanics, which was the first application of BPMs if you look into the literature, excavation, cutting and digging applications. You will see a plurality of application opens up when using the BPM. The rich information that can be distilled out of comminution simulations is visualized on this slide. As you will see towards the end of the animation, the stress in each of the bonds, which are used in between the tracked point particles inside of this large disc-shaped grain, is calculated and used to determine whether it breaks or not. This video already concludes our first section of this unit. Let us now progress to material that contains more details of our flexible particle model.